Welcome to This Explainer. Today, we're doing something pretty awesome. We are taking dry textbook geography and transforming it into a literal, practical survival toolkit. Honestly, if you've ever stared at a dense topographical map and felt like it was written in some ancient, alien language, well, you're exactly in the right place. Just think about this for a second. How is it actually possible to take massive physical spaces, sprawling mountain ranges, winding rivers, dense cities, and shrink them down into a proportional, portable guide that you can literally just fold up and put in your pocket? It's basically compressed reality. It feels a bit like magic, but it's actually a highly refined science. So here's our game plan today. We are going to master 4 essential tools. 1. Decoding the map scale. 2. Measuring distances and areas. 3. Mastering directions and bearings. And 4. The 3 types of north. All right, let's jump straight into tool number 1, decoding the map scale. A map isn't just a rough sketch, right? It is their real world in miniature. And to pull that off, it relies on scale. That's the exact rigid mathematical proportion between the distance on your piece of paper and the actual dirt out there in the real world. Now, cartographers don't just give us one way to figure this out. They actually give us 3 different options. There's the statement method, where it's written out in plain English, like 1 centimeter to 1 kilometer. Then there's the linear or graphic scale. And finally, you have the mathematically elegant representative fraction, or RF. Think of the linear scale as a built-in ruler right on the paper. It has these primary divisions that measure major distances, like big 5-kilometer chunks. But if you look closely past the 0 mark, you'll find the secondary divisions. These break down one primary unit into much smaller, super precise increments. It basically lets you measure out exact fractions of a kilometer with just a quick glance. But what happens if you're navigating somewhere that uses entirely different units of measurement? Enter the representative fraction. It's a ratio where the map distance and the ground distance are expressed in the exact same unit. Because it's completely independent of any specific unit, like inches or centimeters, it works absolutely anywhere. That's why navigators universally call it the international scale. So here's the kicker. If you see an RF of 1 to 100,000, it simply means 1 unit on the map equals 100,000 of those exact same units in the real world. 1 single inch on the map, that equals exactly 100,000 inches on the ground. 1 centimeter equals 100,000 centimeters out in the mud. It is just brilliant in its simplicity. Moving right along to section 2, measuring distances and areas. Okay, so knowing the scale is great for straight lines, but let's be real, nature rarely moves in straight lines. How on earth do you measure a winding river or a twisting mountain road using a stiff, straight ruler? Well, you can't. Map makers actually use this fascinatingly analog method. You literally just grab a piece of thread. You carefully trace that thread along the curve of the river on your map, following every single bend. You mark your start and end points on the thread, and then you just pull it perfectly straight and measure it against your map's linear scale. It's such a beautifully tactile way to handle complex geography. Now, if you want to get a bit more technical, you use what's called an opisometer. It's this highly specialized tool with a tiny spiked wheel connected to a calibrated dial. You simply roll the wheel along the curved line on your map, and the dial records the exact distance. Then you just convert it using your scale. It's absolutely essential when you're tracking a sprawling route across a really complex topographical grid. But what if you need the area of something weirdly shaped, like a sprawling, irregular forest? You use the grid square method. It's math-light and highly practical. You just count the fully covered squares, estimate the partial ones as either 2/3 or 1/3, depending on how much they cover, and add them all up. Boom! You get a highly reliable estimate of an area, and you didn't even need a computer to do it. Which brings us to part 3, mastering directions and bearings. We all know the basic cardinal points, right? North, south, east, west. But if your landmark is 5 miles away, telling someone to head northeast is way too vague. They'll miss it completely. That's exactly why true navigators shift to a much more precise system: angular bearings. A bearing leaves absolutely zero room for interpretation. By definition, a bearing is the horizontal angle between north and the line connecting you to your target. And crucially, it is always measured in a clockwise direction. So instead of a vague east, you are moving at exactly 90 degrees. Instead of kinda southwest, you are locked in at exactly 225 degrees. Picture this. You need to get back to camp before dark. You need your backward bearing. The rule here is incredibly simple, but it's a lifesaver. If your forward bearing was less than 180 degrees, just add 180. If it was more, subtract 180. It's basic math, but it guarantees you won't end up wandering out into the wilderness forever. And finally, part 4, the 3 types of north. Okay, prepare for a bit of a mind bender. North isn't actually just one single place. True north points straight up to the geographic North Pole. But your compass? It doesn't point there at all. It points to magnetic north, which is dictated by the Earth's shifting magnetic field. Fun fact about this, magnetic north drifts so much that airport runways literally have to be repainted and renamed every few years just to keep up with it. Because true north and magnetic north aren't the same thing, a distinct angle forms between them. This is called magnetic declination. And, to make matters worse, it moves. The gap between your map's north and your compass's north is constantly shifting depending on exactly where you're standing on the globe. To help us account for this, map makers actually hide a sort of secret code right on the map: isotonic lines. By finding the line closest to your location, it tells you exactly how many degrees you need to add or subtract from your compass to find true geographic north. And just to keep us on our toes, yep, there is a third north, grid north. Maps are flat pieces of paper, right? But the Earth is a sphere. When you flatten out the globe, which is honestly just an absurd and challenging spatial problem to begin with, you have to draw these straight lines of longitude to make a workable grid. Grid north points along these artificial lines. Navigating accurately in the real world means you have to juggle all 3 of these norths. We live in an era where our smartphones do all this heavy lifting for us. But think about it. If you drop that phone in a river or the battery just dies, do you still have the tools to decode the real world around you? Mastering this analog language of maps isn't just some lost vintage art. It remains an absolutely vital survival skill. So get out there, grab a paper map, and keep exploring.